All right, let's take a look at question number 8. For question number 8, we are to find the integral expression. Just a setup, we're not doing it. To find the volume of a solid where its base is region R, where its cross-section perpendicular to the y-axis is a square. All right, so first thing we're going to do is we're going to write down the formula for volumes of solids with known cross-sections. So the formula is V equals the integral from y equals A to y equals B of the area of the cross-sectional shape A of y dy. So you might wonder, why are we using y's in this formula? Well, notice what the cross-section is perpendicular to. Is perpendicular to the y-axis. Remember when we were doing 1, 2, 3, 4, 5, 6, 7 in the previous clips? The direction of rotation tells you what your variables are. If you are rotating about the x-axis or in the direction of the x-axis, all your functions should be in terms of x. If you're rotating about the y-axis, all your functions should be in terms of y, including your limits of integration should be constant y values. Also, when you're dealing with solids with known cross-sectional shapes, the direction of perpendicularity should determine your variable. So since this cross-section is perpendicular to the y-axis, all our variables should be y. Okay? So keep that in mind. Now, we are dealing with a square here. From elementary geometry, we know that the area of a square is equal to s squared, where s is the side length, right? So this is pretty easy. In this problem, s is going to be a function. You're going to see why in a minute. So let's go ahead and figure out what s is. I'm going to be determining the length of s using two views. Okay, this is going to be the top view, very easy to generate, and then the 3D view is a little bit more involved. Okay, on the exam, you can just use the top view and get full credit. It's easy, but the 3D view, I'm going to do it just to give you a solid understanding of the appearance of the solid that we're computing the volume of. Now remember, the cross-section is perpendicular to the y-axis. So let me just draw one of the squares. This is the base of one of these squares, like that. Okay? And guess what? This is s. Alright? S is going to be a function of y, because you were going in this direction. Okay? So our area, the volume, is going to be the integral from y equals a to y equals b of s of y, the side length as a function, squared dy. Okay, so all I just need to do is find out what function represents s of y, this length right here, and then put it in here, put the limits of integration, and I'm done. Okay, so let's go ahead and determine what the functions are. From the previous problems we did, we know that this function right here, the function on the top, this red one is what was it again? It was f of x equals root x. As a function of y, it's equal to y squared. Okay, we put this as a y and you solve like we did in the previous problem. That's how you do it. All right, and then the blue one is was f of x equals, okay, let's freeze, my thing isn't working. Let's fix this real quick. All right, sorry, my battery ran out there. Okay, so f of x, the linear function, let's remind ourselves what it is. The linear function is x minus 2. So let's write that down, x minus 2. And if you want to write it as a function of y, it's going to be simply y plus 2. Okay? Now, remember everything is in terms of y here, so we're going to be using the functions in terms of y. Now, what is the length of S? What is the length of this segment? Remember we talked about top and bottom in both orientations. If you're going along the y-axis is like your floor, so you're standing on the y-axis. Whereas the top, the positive x direction is your top, and the negative x direction is the bottom. Okay? So to find the length of s of y is simply going to be the function on the top as a function of y minus the function on the bottom. Okay? So can you tell which function is on the top and which function is on the bottom? The function on the top, if you're slicing horizontally, is going to be a linear function, the blue one. And then the function on the bottom will be the red one. Okay? So the length s of y is simply going to be the function on the top, which is y plus 2, minus the function on the bottom, which is a radical function. But in terms of y, it's going to be a square function, the inverse of that, minus y squared. Okay? So that's the length of your, the base of your square. Remember I told you it's going to be a function. So now that we have s of y, the length of the base of our square, we're just going to put it in here. And that will be the volume of our solid, okay? So the volume V is going to be the integral from, now the coordinates of this point is 4, 2. We're going, this slice is going along the y-axis, so you're going from 0 all the way to 2. So from 0 to 2, s of y squared, s of y is y plus 2, the function on the top, minus y squared, the function on the bottom. That's the length of a side of a square, but we're going to square to find the area, and then find the infinite sum of all those respective squares that we have to generate the volume of the resultant solid. Okay? So that's the answer for number 8. Now let me just give you a 3D view just to help you see what this solid looks like. This is viewing it from the top, okay? Just the top view, aerial view of our solid. Now a 3D view, we're going to basically be drawing squares that the base sits in this region. What I did is I rotated my x-axis backwards a little bit so we can have a 3D perspective of the solid. So this is my y-axis, sorry, and this is my x-axis. Okay, so I'm just going to draw multiple squares here just to show you what it looks like. Let me draw this slice. So this slice goes from 1 all the way to 3. That goes the first one. And then we have a whole bunch of squares just sitting on the region enclosed by these two functions right there. Goes another one. It's not perfect, but it just gives you a general idea as to what the region looks like. It's kind of interesting region right there. You don't have to do this on your exam to get the problem correct. I'm just doing this so that you can have an idea as to what the solid looks like. Rather interesting solid. So there you have it. Let's draw that one again. So you start from a square. Let me draw some few ones at the back, just to give you an idea as to what the solid looks like. Okay, so it just goes up like that and then comes right back down. So this is what the solid kind of looks like. The solid of the region that is generated by this equation, and then the volume is basically what this integral expression that we came up with is. Okay, so this is just a visual of our region, and then the area of each square is given by s of y squared as indicated up here. Okay, now let's take a look at question number 9. Number 9 is similar to this, but it's not a square. Let's take a look at it. For number 9, the volume of a solid where its base is the region R, where its cross section perpendicular to the y-axis again is a rectangle with base 5 times the height. So the base is 5 times the height, basically. Okay. All right. So since we're using the same formula, let's write it down again. for number 9, since the cross-sectional region is perpendicular to the y-axis, so the volume is going to be the integral from y equals a to y equals b of the area as a function of y dy. Okay, just like as we did before. Okay, but now let's figure out what the area of the rectangle is going to be. The area of a rectangle is let's use base times height. Is that what was used here? Let's look at it. Okay, base and height. Okay, we're gonna use base times height. Okay, base times height. That's the area of a rectangle. So we're told here that the base is 5 times the height. So if the base is equal to 5, now I'm sorry, let's call the base S because it's on the region. Okay, so if base is equal to S and the length is equal to 5. No, the base is 5 times the length. So the base is also equal to 5 times the height. 5h. Let's go back. So it says base is 5 times the height. Okay. So base is 5 times the height. So if the base is 5 times the height, that implies that the height is going to be 1/5 of the base. I know you can do this mentally, but I just want to show you the algebra that leads to it. Okay, so the height is going to be 1/5 of the base. So if I want to write height in terms of S, that also implies that the height is going to be 1/5 of S. If the base is S and the base is 5 times the height, which implies that the height is 1/5 of the base, and if the base is S, that means the height is going to be 1/5 S. So what does this mean? It simply means that the area of a rectangle is going to be the base, which is S, times the height, which is 1/5 of that, 1/5 S. That's going to be what our area is. So it's going to be 1/5 S as a function of y squared. Okay. Well, let's take the function out of there first. Let's look at simple first. So 1/5 S squared is going to be our area of a rectangle where the base is 5 times the height. Okay. So let me give you a sketch. 1, 2, 2, 3, 4, 5. So a rectangle like this. Yeah, this is elementary geometry, so you guys already know this. So this is the base S, and this is the height 1/5 S. So the area is basically going to be that. All right. So that means the volume of our solid is going to be the integral from y equals a to y equals b of the area. Now is going to be 1/5. S is going to be a function of y, since we're slicing in the direction of the y-axis, quantity squared dy. So this is going to be the volume of our solid. All right. We already know what S is because it's the same direction. So our S is just the top function, y plus 2, minus the bottom function, y squared. So just simply insert it here. Okay, and that'll be the setup. So it's going to be the integral, the same limits for integration, 0 to 2 of 1/5. You can factor out the 1/5, but let me just leave it here. 1/5 times S of y is a function on the top, y plus 2, the linear function, minus the function on the bottom in terms of y squared dy. And that's the area of the region that we're dealing with for problem 9. Okay.